We've all seen them, right? Those incredible videos of robots doing amazing things, making it seem like a fully automated future is just around the corner. But then you look around, and, well, it isn't here yet. So in this explainer, we're going to look past the shiny demos and get real about what's actually happening on the factory floor. We're going to define what physical intelligence truly is. And let's be absolutely clear, the progress is real. This isn't just hype. The entire field has genuinely crossed a major threshold. I mean, with the leaps we've seen in dexterity, in perception, in multimodal reasoning, all those old arguments that robots can't see or adapt, they just don't hold up anymore. The raw capability is finally here.
But that leads us to this huge paradox. If the capability is there, why isn't the world filled with robots? Why are factories still using the same industrial arms they've had for decades? Why do warehouses still rely so heavily on people for the tricky stuff? And those humanoid robots? For the most part, they're still stuck in demo videos and VC pitch decks.
So, what's the holdup? What is the real bottleneck standing between that slick demo and widespread deployment? You know, the common mistake is to think it's all about model intelligence, that we just need a smarter AI. But the truth is so much more complex. Deployment isn't some final step you figure out later. It's the central problem we have to solve from the very beginning.
To really get this, we have to talk about what's called the great divergence between capability and capacity. This is the massive gap between what a robot can do in a controlled lab environment and what it's actually trusted to do reliably, at scale, out in the real world.
And this is where we need to introduce the idea of physical intelligence. It's so much more than just AI with motors. Think of it as the messy, difficult, and frankly brutal integration of AI with the hard realities of the physical world. We're talking steel, hardware, capital cycles, industrial timelines. It's not an installation, it's a collision.
And you can see that collision right here in these two starkly different worlds. On one side, you have the research frontier. It's all about learning, flexibility, and creating those impressive demos. On the other side, you have the deployment stack. Its goals are reliability and predictability, often using boring, deterministic code. Why? Because boring scales. And right now, these two worlds are miles apart.
This gap really shines a light on one of the biggest misunderstandings in robotics, especially for folks coming from a pure software background. And that's this obsession with average performance. In the world of physical systems, focusing on the average isn't just wrong, it's dangerous.
Let's just look at this number for a second. 95%. I mean, in almost any other field, a 95% success rate is fantastic. It looks great in a research paper, great on a slide for investors.
And you know, in a research lab, it is an extraordinary success. A model that works 95% of the time, that's a huge breakthrough. It gets published, it generates buzz, it pushes the whole field forward. It's a massive win.
But then you take that same 95% success rate and you put it into a production environment. Now it's an unmitigated disaster. A system that fails 1 out of every 20 times doesn't just scale poorly, it completely collapses. Every single failure needs a human to step in, it triggers safety stops, it causes expensive downtime. The costs aren't linear, they cascade and compound.
And here's the key insight. In robotics, averages just don't matter. It's the tail, that rare, catastrophic failure, that defines the whole system. Real industrial automation needs reliability measured in basis parts, or parts per million, not percentages. That's why the old, predictable, classical robots still run the world's factories. Their failure rate is understood, bounded, and incredibly low.
This brings us to another huge reality check. The physical world isn't a clean, simulated environment. It's messy, unpredictable. You could even say it's adversarial. And that means we have to grapple with the unavoidable, unbreakable laws of physics.
To actually work in the real world, this physical intelligence has to be split in two. Physics basically demands a 2-layer system. You need a slow reasoning layer. That's where the big AI models live, handling the high-level planning and intent. That's the strategist. But you also need a fast control layer for the immediate real-time physics of motion, force, and feedback. That's the athlete. You can't have one without the other.
And this is exactly why the idea of a purely cloud-controlled robot, while it might make for a cool demo, just doesn't work in the real world. Latency isn't just some software nuisance you can optimize away. It's a fundamental constant of physics. You absolutely need that real-time intelligence right there at the edge, on the hardware, whether the marketing deck wants to admit it or not.
Okay, so the robot itself is already pretty complex, but it doesn't operate in a vacuum. This is where we have to zoom out and realize that the robot itself is not the product, the entire system it has to live inside, that's the actual product.
A robot has to plug into this incredibly complex ecosystem. You're talking about safety certifications, maintenance schedules, the economics of integration, existing human workflows, the inventory software, all the way up to the company's capital investment cycles. A robot that can't seamlessly fit into this whole operational fabric? It's not a solution, it's just a really expensive science project.
Let's just focus on two of these bottlenecks because they are so often underestimated. First, safety. Our entire safety certification system is built for predictable, deterministic machines. It's a total structural mismatch for a system whose behavior emerges from data. And second, maintenance. A robot that needs a team of PhDs to keep it running will never ever scale. The industry is missing a DevOps layer for robotics, the tools and diagnostics for the technicians on the ground.
Now, after laying out all of these challenges, it would be really easy to walk away feeling pessimistic. But that is completely the wrong takeaway. This huge gap between the demo and deployment, it's not a sign of failure, it's a map. It's showing us the new frontier where the real, durable, long-term value in this industry is going to be created.
So where does AI actually move the needle in all of this? Look, it's not magic. It doesn't repeal the laws of physics or economics or the way big institutions work. What it does do is change the fulcrum point. AI can radically bring down development costs. It massively increases flexibility. And it shifts the source of value away from static, rigid programming toward dynamic, learning-based data systems.
And this brings us to the ultimate point. Closing this gap between the demo and mass deployment isn't going to come from one single brilliant insight or a slightly better AI model. The solution is infrastructure. It's the unglamorous hard work of building robust data pipelines, mastering reliability engineering, and creating entirely new safety frameworks. This is going to happen on an industrial timeline, not a software timeline.
The capabilities are here. The capacity is now being built. True physical intelligence is coming, and when it arrives at scale, its impact is going to be far more profound than any single demo we see today. This isn't a product moment, it's an ecosystem moment. Good luck ignoring that.